welcome back again. Our next talk is by Santiago Triana, and it's about inertial eigenmodes in the sun.
Thank you, Uli. Well, first of all, thanks to the organizers for giving me the opportunity to show this work. It's work done with Gustavo Guerrero, Ankit Barik, and Jeremy Requier. And hope Ankit is probably in the Zoom. I hope. Okay. Well, a little bit of motivation. I am actually trained as an experimental fluid dynamicist. So for me, in my eyes, the sun can be considered as a spherical co-ed system with a latitudinal differential rotation. And as some of you know, I come from a lab where we built probably the largest spherical co-ed device. And in that device, when you rotate the inner core a little bit slower than the outer core, you generate inertial eigenmodes in a very clear way. And so this is actually an old result from 2007. And it's probably one of the motivations that I actually had when I decided to look at the inertial waves in the sun, because we still don't know how these inertial eigenmodes appear in the experiment. So the differential rotation in the sun is probably one of the major achievements in helioseismology, all thanks to Jorgen that is here with us today. And it's basically, you have acoustic modes. You can measure the shift of these modes according to the differential rotation of the background flow. And if you make a key assumption here, that if the frequency of the acoustic mode is very large compared to the rotation rate, then you are kind of in business. You can use forward modeling and inverse modeling to figure out the differential rotation of the interior. Now, fast forward 4 years ago, 2018, there was this extremely interesting discovery of Rossby waves in the sun. And you've heard already the talks on Tuesday. And just briefly to recall, they look like radial vorticity waves around the equator. And they match very well the dispersion relation of a Rossby wave. And so here is the dispersion relation of a Rossby wave. But they turn out to be sectoral. So the L or the angular degree is the same as the azimuthal degree, L equals m. And if you use a reference rotation rate of 453 nanohertz, and you use that formula, you can fit very nicely the observed frequencies of these sectoral Rossby waves. Okay, so just a little bit of terminology, because I'll be using it a lot. This Rossby wave dispersion relation is usually derived by considering a thin shell of fluid, neglecting radial motion. So there are no poloidal motions. And you can call them sectoral if L is equals m, and they look like that if you plot the radial vorticity. And tesseral if L is larger than m. And in that case, you can have either symmetry, equatorial symmetry. Okay? Now, fast forward to earlier this year, just at the beginning of the year, this important paper by Chris, that is also here with us, Chris Hansen and colleagues, and they reported yet another set of waves that are shown here in this this one, and you can see it here in using three different methods of detection, which I'm not really knowledgeable to discuss them, but I relay that to Chris. And these are the radial vorticity power signal in the L equals m+1 channel, meaning that these are equatorially antisymmetric vorticity waves. So they call them high-frequency retrograde waves because, well, they are retrograde. They drift in the retrograde direction, they are high frequency compared to the Rossby waves that are a smaller frequency in absolute value. And well, they left the question open because they really couldn't find a good match for these waves. So the question was still open when they published this paper. And I got really curious to see if, why these waves were not like the same as the Rossby waves, or what were they? And well, it turns out that we have a code that we could use to compute inertial waves. And no, let me start the story from the beginning. So this is the observations that reported from the 2018 paper and from the 2022 paper. So these are the sectoral Rossby waves, and these are the HFR waves. So those are the observations that I extracted from the paper. And if you plot the analytical Rossby wave dispersion relation, then you have this very nice line. So it's a very good match, excellent identification of the modes. And we use our eigensolver, and in a nutshell, you get this result. So it's a pretty good match. But, well, this is actually not how it went first, of course. So at the beginning, we tried using the same reference frame as they used for the sectoral Rossby waves, which is this one. And you see the match is not so great. I mean, it's okay, but it's not really good. The trend is nice. But if you use this other frame, what is the so-called Carrington frame, 456 nanohertz, you get a much better fit. But then, of course, nothing is good always. And then you get that the sectoral Rossby waves do not match so well. So what do you do? Well, you embrace the question. So this could be an indication that precisely this set of waves and this other set of waves are perhaps sampling different regions in the sun that are rotating at slightly different rates. And okay, so let me just give you a brief idea of what we do, like how do we do our calculation. So it's actually quite simple. It's a uniform density model. There is no heat, there is no magnetic fields, and there is no nonlinear term. So we basically solve the Navier-Stokes equation with viscosity in a spherical shell with delta. And well, the effective viscosity, or the viscosity of the flow, is controlled by this number, the Ekman number. And if you assume that there is an harmonic motion, you can set this, use this as an ansatz, replace that there, and set this eigenvalue as the damping and the frequency. And you use a pretty standard spherical harmonic expansion, a poloidal toroidal decomposition. And this is a little bit different from what is usually done. Normally, in the radial direction, you use Chebyshev polynomials. And we do too, but with a slightly better version that is the Gegenbauer polynomials. That is kind of like a generalization of Chebyshev. And with that, we convert the problem into a generalized eigenvalue problem, and we use stress-free boundary conditions. So this is the result, basically. In the horizontal axis is the width of the shell, and the vertical axis is the frequency. And in color is the damping. So the more red, the less damped the mode is. And I also put the size of the symbol to reflect the damping as well. So the more red, the bigger the mode is, and the less damped it is. So it's more likely to be excited if you were to force it. And you see these lines here. There are like very, very small damping. You see these other lines over there. This is just an example for 3 different M numbers, azimuthal M numbers. Okay, and this vertical line is the convection zone width of the sun, the actual one. So 0.29. the dispersion relation from the Rossby waves predicts these frequencies precisely. If you set L equals 7 and L equals 5 at the same number, predicts this frequency. So I plotted these straight lines over here and here for the three M numbers. And you see that the frequencies of the dispersion relation match very well only if the shell is thin, which is not surprising. But what is maybe more interesting is that as the width of the shell increases, that frequency really deviates a lot from the Rossby wave dispersion relation. Oh, sorry. Now, these are the observations that I extracted from Chris' paper. These are the observations for three different M numbers. And this is the overall picture. So they had identified modes from M equals 4 to M equals 14. So I did the calculation for a number of M numbers. And you see these places where they intersect the line for the convection zone width over here. And these are the points that I plotted actually in this plot. So you see there are sort of like a main branch and then some other secondary branches. And you see also the signal of the signature of the tesseral Rossby-modes. And that's essentially what it is. So the M trend is similar to observations. The frequencies match reasonably well. And this is not shown here, but the L equals M plus 1 component in the spherical harmonic decomposition matches also the observations. So all these modes, I'll show you in a moment how they look like. So this is an example of two modes, the one sectoral Rossby mode, the ones that were observed in 2018, and this is another one in the main branch mode that was observed by Chris. And you see, in this case, you have some reasonable flow near the surface, but you also have substantial flow in the interior. The sectoral Rossby modes, in contrast, they don't have so much motion in the interior. This, I don't know if you can see the scale, it's a little bit small, but it's really tiny, the radial velocity here. So the signal is actually super, super small. Most of the amplitude of the mode is just at the surface. But this mode is actually, it kind of hugs the equator more than this one. This kind of avoids the equator. And so in essence, they are really sampling slightly different regions of the sun. And I just put here the differential rotation of the sun as the background, just to give you an idea. But maybe a much better case can be made by considering another mode that is not reported by Chris, but is actually reported by Laurent Guisson in 2021. It is, well, actually by Hathaway and Upton in 2019 too. They reported this so-called high latitude Rossby mode. It's an M equals 1 mode, but it has more than one L component. That mode doesn't really match well the frequency, but as you can see, this mode actually lives inside the tangent cylinder, so more towards the north and south to the polar regions. So it's really not sampling the equatorial region as opposed to these other modes, for example. And it looks like this. It looks like a spiral. But so if you were to consider that this mode only lives in the tangent cylinder, and just imagine for the sake of the argument that it doesn't have any amplitude outside the tangent cylinder, then that mode, if you Doppler shift it to that region where it mostly lives, then it will have a frequency of about 86.4 nanohertz, which is very close to what is observed. So it's actually a pretty good identification of the mode as well. And notice that there is a spiraling that is not due to differential rotation or anything like that, because this is a uniform rotation model, and we have no latitudinal heat variations, nothing like that, nothing complicated. So the spiraling comes by itself in this linear calculation. Okay, so how do they look like in the interior? For example, the main branch looks like this. This is the integrated kinetic energy as a function of the radius. So theta and phi integrated. And you see that the radial component, the blue part, is really small, which is, well, not surprising because of the boundary conditions. You said non-penetration. But the toroidal and consoidal components are more or less similar. But in the interior, the radial part takes over. It's really larger than the other two, which is completely in opposition to the sectoral Rossby-mode, which is always toroidal, although its amplitude decreases as you go further in radius. And this high latitude Rossby-mode is even more special because it's purely toroidal most of the time, but it has substantial amplitude in the interior, which is actually quite good if you really want to sample the zone deep in the convection zone. And this is what the spectral amplitudes look like. So this is the spherical harmonic degree, and in green is the toroidal part. And you see that this one, for example, this is for m equals n8. So the L equals 9 is the highest contribution to the mode, although there are more contributions. So it's not just that one. The sectoral Rossby-mode has, well, as you can imagine, it has the same L equals m. This is the main contributor to the mode, but the other ones are relatively smaller. And the high latitude Rossby-mode actually has many components that are similarly, have similar amplitudes. And this is, for example, from the paper by Hathaway and Upton, where they show the power in the different L's. As you can see, that they are all populated, the odd ones, or, well, I don't know if it's correct, but it actually matches more or less, well, qualitatively, the different contributions of the different L components. Now, where did the tesseral Rossby-modes go? Because this is one of the open questions, right? Why do we observe in the sun the sectoral Rossby-modes, but not the other ones? So I'm trying to give a clue with these figures here. This is the equatorial antisymmetric vorticity modes that contain the HFR modes that Chris observed. Although I'm not plotting them in this part, I'm plotting only the low frequency component, or the low frequency modes. And these are the equatorial symmetric vorticity modes. And this one in particular is the L equals m, and is a true sectoral Rossby-mode. And this is the damping of the modes, topic the frequency, and the horizontal axis is the width of the convective zone. And you see that as soon as you have some substantial or some appreciable width, the damping just increases dramatically. And same for the other kind of modes, except the sectoral Rossby-mode. The sectoral Rossby-mode is happily, nothing happens to it, and it kind of even likes it. The frequency, the damping is even a tiny bit smaller. But the other ones, the ones that have L larger than m, they change their frequency noticeably, and their damping increases dramatically. So this is probably one of the reasons why you don't observe these modes. And moreover, they kind of cease to be completely toroidal. For example, this is the ratio of the poloidal to toroidal kinetic energy. And you see that the modes have substantial poloidal component, and in this part too, except the true sectoral Rossby-mode, which is very small. I couldn't really plot it there. I should have used a logarithmic. And, oh, sorry. And this is probably related to a puzzle that appeared like about 20 years ago, where in the community, the stellar astrophysics community, were puzzled by apparent disappearance of the R modes in the isentropic stars. And I think, I might be wrong, but I think the answer is that they were probably confused and they mistook these modes that have substantial poloidal components as actual Rossby modes, which they are not because of the poloidal component precisely. And in this plot, I'm also putting the HFR modes, and you see they have a substantial poloidal component. So the kinetic to the poloidal to toroidal kinetic energy is about 1. So this terminology of R mode is really questionable. It could be useful if you really are talking about a true, well, you know, when I went to school, they told me a Rossby mode is toroidal. You know, that's what I learned. And so I just wanted to make it a little bit as a tease by putting this meme. That because generalized R modes is a term that is used commonly in the literature, but it's really misleading. They are just inertial modes. Okay, and just a little bit more before I finish is these modes that I show here, these are the HFR modes that Chris reported. But according to this model, there are these other modes up here that are the tesseral or tesseral-like Rossby modes that have more less damping than these ones. So are they there in the sun? Do we see them? We see them in the laboratory, actually. And this is something that I worked on for quite a bit, as I mentioned at the beginning. And I'm going to show you a picture or a movie. It's too bad that it's choppy. But what you see here is a bunch of these tesseral Rossby modes excited by the differential rotation of the inner core. In this case, the inner core is rotating just a little bit slower than the outer core. And okay, I think, so I was actually posing this question to Chris, like what is the signal that is observed here? And Chris was telling me that it's really hard to say if there is anything really there, but it could be that some signature of the tesseral modes is really buried in that region. So it could be. Anyway, so to summarize, a simple model can take you a long way. The HFR waves reported by Christensen are recovered very nicely. They have appreciable radial flow deep in the convection zone, so they are really promising to diagnose flows deep in the convection zone. And the tesseral Rossby modes, maybe we should think about them. I mean, like, they might not be Rossby modes anymore. And well, that's pretty much it. Inertial modes are really intriguing, and I think this is probably a really great opportunity to use these modes and perhaps learn a little bit more about the interior of the sun. That's it. Thank you.
Well, thank you very much. Now it's time for questions or comments. And Johannes.
Yeah, thanks for the very nice talk. I was a little bit surprised. You said the density is constant, so there's no stratification.
No stratification.
Could you, and nevertheless it matches? So you're saying it would have no influence, or do you have any idea? Yeah.
The way I explain it is that since the motion of these modes is here. Oh, I'm showing something. Oh, okay. It's mainly toroidal at the surface, so perpendicular to the stratification. So that's my guess. That's why you don't really affect them by the pronounced stratification near the surface. Well, this one's, yeah, surely, but in the interior, the density contrast is not so much.
I see many hands. I don't know who was first.
Thank you very much for your nice talk. Just looking at your fitting at the beginning, were you tempted to use a differential rotation in your inertial wave code?
This is planned, although there is already a code that, or a model that Yuto Becky already devised. And I'm not sure how the fit improves or worsens, but we also wanted to include differential rotation in our code. It's something that we have not done.
Right.
It's a long-standing project.
I was going to say, it's very easy to do, right? As long as the rotation rate depends on the
exactly,
radius.
yes.
Yeah.
But it's actually a good point. So we really want to have something like, sorry to go back. We want to have the same as this for inertial waves. That's I think, but we have no way of doing it at the moment. Not even numerically.
Yeah, I mean, with the theta, that's the problem, right? Because then you're going to get away from your spherical harmonic decomposition.
Yeah.
Okay, thank you.
Thank you for the talk. I have one comment and one question. So my comment is that, so the high frequency retrograde mode is, as you said, a very non-toroidal. So I think one very important future application is, so they should be very sensitive to the superadiabaticity, the background.
Yes.
So one possible application is to check that dependence to infer the delta in the sum. And my question is, so in this slide, the high latitude mode seems, I think it has the wrong the spiral direction. So I wonder how it changes with the thickness of the shell as you change.
Yeah, I didn't look at the pattern as the depth changed. So you're saying that it's spiraling in the wrong direction? Yeah. Ah, okay. Well, I guess I cannot say much. That's the result of the linear calculation. So, yeah.
Okay, Bruce. Maybe meanwhile, Radostein can start to set up.
Yeah, Santiago, I guess the question about the density variations is not so much really the changes in densities as things move horizontally, but rather the fact that associated with some velocity there will be a different momentum. That momentum would be different according to the density. And so I think the horizontal motion is only part of the story, and it seems like it's possible that the structure of these modes could change a little bit if you were changing the density as a function of radius.
Yeah.
So is this something that could be done with this formulation? Could you actually try to include those effects?
Yes, we can certainly. It's actually in the pipeline. We want to go and use an elastic approximation to have a more realistic profile. But again, the model by Yuto already includes this. So that's well, it's certainly the more sophisticated version, and so probably with the help of that code, things can be answered. But it's good to have at least this baseline as a baseline, to understand what's coming from a simple linear model. Okay, thank you.
Hi, yes. When we made observations of this, we couldn't find a radial component. However, your model suggests that there should be a radial component to these modes. Are you able to comment on possibly, so the toroidal flows were around 1 meter per second. Are you able to comment on how the amplitude of the vertical flows, just so like as an observer we could maybe think if it's possible to detect these things or not?
Yeah, I would think that since these are already at the limit of detection, right? So these are really, so the radial flows deep in the interior are really small. I mean,
So
yeah,
impossible
you can
to
actually,
see.
you can, it's stopped. But yeah, the radial component in the interior, although appreciable, is really smaller than what you observe at the surface, even for the toroidal, the horizontal part. So I don't think, yeah, no chances of observing it.
So let's thank Santiago once more.
Thank you.
So last talk before lunch will be by Radostin Simitev, and he will talk about not inertial modes, no, thermocompositional convection in rotating spatial and dynamos in rotating spatials.